Hello, my name is Frank, and we're going to be talking about some exercises with the linked list. So we discussed the linked list data structure briefly about in the previous video, and so now we're going to be talking about actual actions we would be doing with a linked list in an actual computer. And so here we can see the linked list in the data structure forms, right? So we have the head, and we have a couple of reference nodes. We have one reference node from the head, one reference node from that node, and so on and so on. So this is the basic linked list in a computer format. In order to reference this linked list, we always have a pointer to the head. So we always have a reference to the head pointer, and we store that in memory. And essentially everything we will be doing with the linked list will come from this pointer. So basically, we'll use this pointer to perform any logic to traverse through the linked list, to find an element in the linked list, or to add or delete an item in the linked list. And so let's sort of talk about making these modifications to the linked list. And so in order to traverse the linked list, first we have to create a second linked list, or a second pointer. And let's call it a traversal pointer. And making a copy of the traversal pointer, we can begin to dereference these nodes. And so from the head, because we'll remember each node has data and a pointer, we'll use the pointer from the head to get access to the second node. And now, once we've dereferenced the pointer reference from the head node, we now have access to the second node. And in order to access the third node, we reference the pointer again, and then we assign that value to this traversal pointer, and now we have access to the third node. And once we are at the third node, we have data, pointer, and this node. We reference the pointer, we assign it to our temporary traversal pointer, and then we're able to get access to the fourth node with the pointer. And then if we do this again with the fourth node, we'll have access to the end, which is null, because the fourth node is the last element in the list, so it will be pointing to null. So we'll call this the tail node, and it doesn't point to anything. And that's how we'll know we have reached the end of the list. And in order to add an element to this list, we'll have to reach the end of that list to append an item, or we can keep track of a tail node or tail pointer, and by having two pointers, one head pointer and one tail pointer, we'll be able to easily add elements to the end of the list. Because we need a reference to this node in order to assign the pointer value to a new node. And if we wanted to add an element, for example, in the middle of the list, we will have to actually traverse it or assign a new temporary or like create a new pointer. So similar to what we did with the tail pointer, we could create another pointer if we wanted to add elements to the middle of the list. That's essentially traversing and adding items to the linked list. And so if we wanted to delete this node, we would need three pointers, essentially. We need a pointer to before the deletion node. We need a node after, or we need a pointer to the node after the deletion node. So it's important to note that we need all three of these node pointers because once we delete this node, we're not going to have access to this node anymore, because each node is used to gain access to the next node. So we need to temporarily store all three of these pointers together. And so let's go ahead and delete this node. So we're using this deletion pointer. And then once we've deleted this node, we don't have access to the reference anymore because it's gone, right? This node pointer is gone. That's why we've stored this third node 3 pointer, which is essentially a pointer after deletion node. And then we go back to pointer before deletion node, and we reference it instead of to the deleted node, we reference it to the pointer after deletion node. And so those are the three main activities to do with the linked list. It's traverse, add, delete. And so traverse can also be like find. The difference would be that once you've in the traversal, you'll add a check, some logical statement to find some either value in the node or a number. So like the position of the node in the linked list. And so why would you use a linked list over an array? So I think it's important to think about an array. If you wanted to add items to an array, you have to reallocate an entire section of memory, because an array is a contiguous series of values. They're all connected in one block of memory. Whereas with a linked list, these nodes that are pointing to a new node don't actually have to be in memory right next to each other. They could be separate. So adding an item to a linked list is a lot easier to do than adding an item to an array. And so that's an interesting concept. Now, in Java and a lot of other languages, there's an array list, which we won't go into here, that sort of tries to combine the best of both of these data structures of a linked list and an array, very similar to basically having a pointer to each node. But we'll discuss that in another video. Okay, and so let's talk about the time complexity of this. So in order to find, add, or delete an item from the linked list, it would take linear time, n being the number of nodes in the list, to find or traverse the linked list, because the only way to go through these items is to go through them one by one. That's the only way to traverse a linked list that only has a pointer to the head. If you're trying to add an item to the linked list, so I want to clarify, if we're specifically only adding the item to the linked list and we already have reference to the node we want to append it to afterwards, that is constant. Disclaimer being, if you're trying to add an item in the list where we don't have reference to that node, then you will have to perform the find traverse activity, which is linear time, O of n. Specifically, adding and appending is constant, and specifically deleting an item is constant. But typically, in order to perform these activities, you need to gain access to the area that you're adding or deleting. So typically, it will become a linear activity of time complexity if you only have reference to the head pointer, which is a reason why a lot of languages like Java use an array list to gain a reference to other items. So that's a trade-off of space and time. And we'll go into that further. But for now, the space time complexity, the most important things to know are, for append / add, it's a space complexity of 1, constant. It's constant time. Delete is O of 1. It's constant time. The space complexity, or it's the time complexity, is O of 1, and the time complexity of traversing slash finding an item is O of n, n being the number of nodes in the list. Yes, and so that's essentially all the activities in a linked list, and these are some of the exercises that you can do with a linked list, along with the time complexity to perform these activities. Thank you.